It's simply the sum over all the deterministic algorithm it may call of the probability pi that I choose this algorithm times the cost of ai given that I'm running over instance ij. And this is Cij, and this is simply P times the column vector Cj. Okay? So now I have here Cj, the worst instance for my randomized algorithm. Okay, and I'm looking for, so this is column. So for this instance here, you have all the cost of all the deterministic algorithm. Okay, and if you average it over P, then you get the cost of P, of algorithm AP. Okay? Because what we want is the best randomized algorithm. Okay? So what is the cost of one randomized algorithm? The cost of one randomized algorithm is that you fix the P here that tells you what is your distribution over all the deterministic ones, and you pick the column, the worst instance, okay, the column here, that maximize this average cost. Okay? And now what you want is the best randomized algorithm. So you minimize over all P's this quantity. Okay? So now what do we need to prove Yao principle? It's the following. Yao principle is simply saying the following things. So it's equivalent to, let C be a matrix. What we want to prove is that the mean over P positive such that sum of the Pi equals to 1 of the max over J of P times Cj is at least, remember that in fact it's equal to, but we won't be able to prove it now. It's an interesting proof, but it requires a lot of work. Is at least equal to, you can exchange these two, max and min, to the mean, no, max, oops, sorry. Max over Q positive such that sum of the Qj is equal to 1 of the mean over I of Ci times Q. Okay, that's what we want to prove. If we can prove that, then we have Yao principle. This one, this is a column, this is a row, this is a row, this is a column. Okay, everybody agrees that this is what we need to prove? Okay, so let's prove it. So in fact, it's quite trivial. Why is it trivial? It's simply because, first, it's true, and second, because I hope that I will be able to prove it. So basically, what does this mean? Why it's morally clear that it's true? It's because here you take the max first and then the mean. Okay? So here you maximized, and then you try to minimize it, but it's too late. It's already maximal. Okay? And here, you do the exact opposite. Okay? You first minimize it, and then you take the max, but it's too late. You've taken the mean. Okay? So that's why this inequality is easy. Proving the converse is another thing. Okay? Proving that it's equal, it's much harder. Okay? But proving that this inequality, which is the only one that we will use, it's good enough. Okay? So how do you prove that? Well, let's just do it. So the first thing that you can remark is that this thing is larger than the max over Q, in fact it's equal to the max over Q positive, sum over Qj equals to 1 of the P CQ. Why is it so? Why do you have this equality here? Yep.
Because you take the Q such that it is equal to the column with one on J.
Yes, because this is simply equal to P times Cj times the vector columns 0 at the... Okay, so this is just multiplying by this vector. Okay, so this gives you that this is less than that. Okay, but in fact it's equal. Why? Because this is maximum. Imagine that you have, look at all the rows of P times C. So P times C is a row vector. Okay, so this is a row vector. This is a row vector here, P times C. Okay? So, what is P times Cj? P times Cj is the jth value of this vector. Okay? So, when the average of this coefficient is maximum, is when you just choose the maximum value of this vector. Okay? So, choosing the maximum value, so what is that? That is the average value of the coefficient of P times C given the weight Qj. Okay, so you give the weight Qj, you weight each coefficient of the vector P times C with the weight Qj. And when is it maximum? When you put all the weight over the maximum element, the maximum value. Okay? So this thing is exactly the max, this thing here is exactly the max over all the possible Q of that. Okay? So you can do the exact same thing on the other side. On the other side here, the minimum here of CIQ is equal to the minimum over all P positive sum of P equals to 1 of P CQ. Why? Because this is equal to the vector 0, 0, 1, 0, 0 CQ, where it's the ith position here, where there is a 1. Okay, so you have that this is larger than that, and to have equality, when is it minimum? It's when you put. So this is the average value of C times Q of C times Q with weights Pi, and when is it minimal is when you put all the weight on the minimum element of this row vector, of this column vector, sorry. Okay? So basically, what do we have now? What do we want to prove now is that the mean over P positive sum of Pi equals to 1 of the max over Q positive sum of the Qj equals to 1 of PCQ is larger than the max over, I can exchange the mean and the max, sum of the Qij equals to 1 of the mean of P positive sum of the Pi equals to 1 of PCQ. Okay, I can either take the mean over the row and then the max over the column, or the inverse. It will be the same. Okay, so but what we will prove is this sense only. Okay, so why is it true now? Well, where is it true? So that's where I will be lost. That's for sure. So why is it true? So why is it true? It's simply because so what I will do is simply the following. So let's consider P star that minimizes the max over Q positive of P CQ. Okay, I'm just considering the minimum P here, P star. Okay, so what do I have? I have that this quantity, the min max of P CQ, is equal to the max over Q positive of the P star CQ. Okay? But this is clearly more than the max over Q positive of the sum Qj equals to 1 of the minimum over all P. Yes, I made it, yeah. Of the PCQ. Okay? So I'm good. It's proven. Yes, exactly. That's what I want to prove. And this is what I've proven. Okay? So I take the P star that realize the minimum. Okay? So what do I have? I have that the min max of PC is equal to the max over Q of the P star CQ. And now I say that, okay, but if I remove it, instead of taking P star CQ, I take the mean over P of P CQ, then it's less. Okay? And then I'm good. There is nothing to prove, that's the problem. That's, this is trivially true. So the mean over P of the max over Q of PCQ is equal to the max over Q of P star CQ, because I chosen the P star that realize this mean here. Okay? But now this quantity here, this one here is at least the minimum over all P's of PCQ. So I just replace it here, and then since the max is an increasing function, I'm still good. Okay? So the perturbing thing is that in fact we can prove that it's equal. Okay? And this is highly non-trivial. And it requires some call to analyze to real analysis or even complex one. I don't remember. And so it's not a trivial thing. But what does it say? What's the consequence of it? Basically, is that there exists an optimum strategy P star Q star. Okay? Yep.
So the equality is true for all problems? Or
Yes.
it is,
Any matrix.
any problem?
Any matrix. It's true for any matrix. So this is called the minimax principle. Why is it so? Why is it related to game theory? So basically, here what we are playing is a game between instances and cost. The algorithm wants to minimize its cost. The instance wants to maximize its gain. Okay? So the algorithm pays the instance. The instance wants to maximize its gains. So what are looking for the instance? It's the worst instance for the worst algorithm, for the best algorithm. Okay? They are trying to maximize their gain in the worst case. So they want to choose the column here such that the best algorithm cannot do good. Okay? Pays the maximum. The minimum algorithm will pay the maximum. Okay? So I'm trying to maximize that. But the algorithm is exactly doing the opposite. What does he want? He wants to choose the row such that whatever the instance is, the cost is minimum. Okay? So imagine that you play paper, scissors, stone. The game where you have to choose paper, scissors, and stone. Okay, and you put here who pays what this algorithm, what this player paid to the other player. What does the minimum, what does the minimax fundamental theorem says? J'entends que vous, moi, je m'entends même plus parler, moi. Donc, what does the minimax fundamental algorithm says is that basically there exists an optimum strategy for both players. That means that there is a P star here, a Q star here, such that this Q star realizes exactly the best cost this player can hope, and this P star realizes exactly the best cost this player can hope. Okay, and this is a very strong assumption. Okay, so basically what you can do is that in this kind of game, where it's called zero sum because what this player earns is exactly what this player lose. So basically the amount of money that both players have does not change along the game. Okay, you just transfer money from one player to another. Okay, for these games, there exists an optimum strategy for both players at the same time. The one that minimizes the loss here is exactly the one that maximizes the cost there. Okay, so basically, if you choose a random strategy, then it's good for both of them. Okay? So this is another relation to game theory here. Okay. So now let's go back to our problem. Okay, so what does this mean? What does this Yao principle mean? It means that if you want to get a lower bound on the cost of any randomized algorithm, we just need to find a bad distribution of instance for deterministic algorithm. Okay, so we pick a bad distribution of instance. We show that any deterministic algorithm will visit at least this number of leaves, and this number will be a lower bound on the cost of any randomized algorithm. Okay, this sounds like magic, but it's trivially true. Okay, that's yep, it's just conceptually difficult to get, but okay. So let's try to get some bad instance for our problem. Okay, so since we are very short on time, we will just try to find an easy instance to analyze. Okay. So what is a good candidate? Let's say what would be a very easy instance. It's just an instance where things do not change from one level to another. Okay, so this will be easy to analyze. Okay, and will already give the good lower bound. So what do I mean by that? First, this OR entry here, it's nasty because why? Because we it's not symmetric. Okay, well, there are two kind of level. It's tedious. Okay, but thankfully, if you plug value here, what you discover is that it's simply the same tree as this tree here. It's exactly the same as that. What is an AND door? An AND gate? An AND gate, A NAND B is simply the NOT of A and B. Okay? So why is it true? It's simply that on the right side, it's simply X and Y or Z and T. Okay? And clearly, on the other side, what is it? It's simply the NOT of not X and Y and Z and T. Okay, so clearly these are these are equal because the NOT of the end, simply you use simply that that is equal to NOT of that. Okay, we just choose that, and we have the equivalence between these two